Next, we're going to take a look at a couple of examples in three-dimensional space. So the first question we're going to ask, it looks almost exactly like the question we asked on the previous page at the beginning. We're starting with a non-zero vector, a single non-zero vector, and saying what is its span? Okay, so we got a non-zero vector v. What is the span of v? The only difference is now this vector is three-dimensional rather than two-dimensional. So the answer is going to be the same, actually. It's just that the answer is going to live in three-dimensional space rather than two-dimensional space. So rather than draw the pictures myself, my three-dimensional drawing leaves much to be desired. In fact, it's quite a challenging thing to do. So I borrowed from the text here and took a couple of screenshots just to make things a bit easier. But you see what happened. I'll kind of do some annotations on this picture. If you start with a single vector v that's non-zero, well, then you can draw it, right? That's what they've started with here. You've got the vector v. And if you interpret that vector as a point, then by taking multiples of that point, the positive multiples of that point are going to give you all, if I take if I take scalars that are greater than positive 1 and multiply them onto v, it's going to move the point in this direction. And if I take positive scalars that have absolute value less than 1 and multiply them onto v, that's going to move this point in this region here. But then if I multiply v by negative scalars, well, that's going to move this point over down into this portion of the line. But in the end, if I let the scalar vary over all the real numbers, I take all the possible multiples of v, eventually I'm just going to get all the points on this line. I'm going to generate the entire line that way, just like we did in the previous page, right? We kind of went through this in detail in the two-dimensional case. The reasoning is the same. The only difference is you're going to get a picture that's in 3 dimensions instead of 2 dimensions. Okay, so that's what happens there. In 2 dimensions, or pardon me, in 3 dimensions, when you take the span of 2 vectors, well, that's when things really get interesting, especially when those 2 vectors are not simply scalar multiples of each other. So let's start at the beginning here and set things up. So we've got 2 vectors that are both three-dimensional vectors. We'll call them u and v. We're going to make some assumptions here. We're going to assume that they're non-zero, and we're also going to assume that neither of them is a scalar multiple of the other. So it's enough to just say where u is not a multiple of v. What we want to rule out is we want to rule out the case where both of the vectors point in either the same or opposite directions. We want to have a situation that really does look like the picture that you see here. So you got a vector u that's pointing away from the origin, is drawn as a position vector, and then you've got some other vector v that's pointing in a completely different direction. So what happens? What do you get if you take the span of those two vectors? Well, the answer is already written here for us. It says that you're going to get a plane through the origin, and you can see they've even kind of drawn a plane. There's this sheet of paper here. I'm just going to temporarily outline this in blue. This slanted rectangle, or it looks like a parallelogram if you think of it as a two-dimensional object. All it is just supposed to be kind of a slanted piece of paper. That's how you sketch a plane in 3 dimensions. Don't let the boundary fool you. It's not a closed finite surface. It goes on forever in every direction. But if you try to draw it without drawing a boundary, well, good luck being able to see it, right? The only reason it's drawn as having this boundary is so you can actually see it. Okay, so that's the shape that is determined by these two vectors if you were to take all the linear combinations of it. Or pardon me, if you were to take all the linear combinations of u and v. For example, here's one linear combination of u and v. It's u plus v. Okay, that's one example. But if you take all the other linear combinations, you're going to generate that whole plane. Now, that's something that might not be so obvious to see, okay? So in the next video, what I'm going to do is I'm going to fire up GeoGebra and show you a little bit in more detail how that plane gets generated.